Welcome to MEI Modelling with Algorithms. We're on the topic of Linear Programming 1, Introduction, and this is video 1.2, Graphical Solution using the vertex method. Now, we saw in the previous video how to formulate a linear programming problem from a wordy description, and we talked about how we identify variables that we can choose the values of in order to either maximize or minimize a objective function. Now, if we happen to have only two variables that we can choose between, then a nice way to think about what's happening is to actually plot a graph. Now, the constraints that we have, and in linear programming they always are linear in form, linear inequalities, so each one of those constraints will be represented with a straight line, and the side that represents the values that are not actually allowed because something is being exceeded, a resource is being exceeded in terms of its limit or what have you, they will be shaded out. Now, it's important to get this convention right, because depending on what you've been doing at GCSE, you may have seen before inequalities represented by shading the region that does satisfy the inequality. Now, when you've got several different inequalities together and you want to show the region that satisfies all of them, it's actually a lot easier to adopt the convention of shading out the unwanted stuff, so you're just left with the unshaded stuff behind. It's much easier to do it that way, so that's why we do it that way. And what that will leave us with is a region of values for those variables which they can actually take, and that is called the feasible region. And whatever our result, whatever we decide is our optimal solution, it must lie obviously within that feasible region. So suppose we've gone through the process of interpreting our worded problem and we've formulated it as a linear programming problem. So we've chosen two variables, x and y, and they will generally represent a number of types of a particular thing that is going to be made in the production process. So in this case, we're obviously dealing with sheds that are being made. So x is the number of shed type A that are going to be made, and y is the number of shed B. And we've got an objective function. Again, that might be profit or what have you. In this case, the objective function is 60x plus 84y, and we're trying to maximize that within the feasible region, which will be defined by the constraints. So the constraints which have been formulated are these: 2x plus 3y is less than or equal to 30, 5x plus 5y is less than or equal to 60. And remember, there are always these natural constraints, meaning that the variables can't be negative. So now that we have those constraints written down, we can then plot them. Now, in terms of plotting straight lines, it's a fairly straightforward thing to do. It's worth just noticing that the easiest way to plot a straight line when it's given in this form, rather than trying to rearrange it to y equals mx plus c, it's actually much easier if you just think about where it crosses the axes, because if I set x to 0, then I can see that I've just got 5y equals 60 and therefore y equals 12. So that tells me that this line crosses at 0, 12 on the y-axis. If I let y equals 0, then I've got 5x equals 60, and I know that it crosses at the x-axis at 12 as well. So you can see that this red line here is the line 5x plus 5y equals 60, and we can do a similar thing with the other inequality here, or the other equation representing the boundary of the inequality here, 2x plus 3y equals 30, and we get this blue line. Now, the first thing we can do always with linear programming when we're doing a graphical solution is deal with the requirement x and y are both greater than or equal to 0. Now we're shading out the region that is unwanted, so there we go, we've shaded both the left of the y-axis and below the x-axis. For this inequality, 2x plus 3y is less than or equal to 30, we can choose a test point that's on one side of the line or the other and see if it satisfies it. Or you could just think about the fact that both 2x and 3y are things which grow and get larger as x increases and as y increases. So there's a sort of direction of increasing value for that left hand side, which will be going in a sort of upwards and right direction. And so this thing is going to be smallest when x and y are both small. So again, that can also convince us that the region that satisfies this inequality is the one which is below this blue line, and that means that we're going to shade the stuff which is above the blue line. Now if we do a similar thing for the other inequality, there we want to keep the region which is below that line, so we'll shade out the stuff above it, and then that leaves us there with our feasible region that we can see there that's still white. Now anything that's going to be a solution to this problem therefore is going to be somewhere in that region. Now you might want to have a think about this. Where, I'm not talking about precisely where, but just in terms of what sort of place within that region do you think we're going to find the maximum values of p? Remember that p is a linear function as well, so as well as the constraints being linear equations, the objective function in linear programming is always linear as well. So the only places actually that could be possibilities in terms of maximizing the objective function are going to be these vertices of the feasible region, and in this case we've got 4 of them, and we can find the coordinates of these vertices by solving the simultaneous equations that represent these 2 lines that make up the boundary. So these are the 4 vertices that we have here, and what we can do now is just do an exhaustive test on each of those 4. So at each of those 4 places, each of those represents a value of x and a value of y. We can put those 2 values into our objective function and see what the value is, and the one that gives us the largest value for the objective function is the one which is going to be our optimal solution. So we're going to be looking at the value at each of the vertices, and here we can see the calculation that has been done. So the objective function was 60x plus 84y. So for each of those 4 pairs of coordinates we put those in, and what we can see is that at that 0.66, that's when we've got the largest. Now that is purely because of the numbers in the objective function. So that's 60 and that 84. If they were different numbers, it's perfectly possible, certainly, that any of these 3 could have been the largest of those numbers. So we really do need to check all of them. We could have anticipated that 0, 0 was never going to be the one that maximized it, because both of these are positive coefficients. So once we've done this, we need to interpret this in the context of the original problem. Now we don't really know in this case the details of the original problem, but we do know that the x and y represent numbers of sheds, so at the very least here we can say that we'll get the maximum value of p of 864 by making 6 sheds of each type. So it is important where you can to interpret that in real life context, especially if the question has required you to do so. Now we're just going to talk briefly about minimization. We're not going to do this example completely from start to finish, just remark on a few things. I mean, really minimization isn't any different from maximization, other than that you're trying to find the smallest value. You can see here an example of what the feasible region may look like. Depending on the direction of the inequality signs in the various constraints that we have, it is possible that the region might be unbounded. It doesn't have to be, but it might be, and that's not a problem in a minimization problem, because actually it's, you know, the further we go up in that direction, the larger the objective function is likely to be. So in this case we'd be looking at vertices like this one here, and testing those vertices in the same way to find the one that gives us the smallest value of the objective function. So that concludes video 1.2. So we've seen a little bit about graphical solutions using the vertex method. In the next video 1.3 we're going to see an alternative method called the objective line method.